Cool. Hey everyone, my name is Luke Metz. I'm going to present our work on practical trade-offs between memory, compute, performance, and learned optimizers. Is it still quiet?
It's okay.
Yeah, you can continue.
Okay. Cool. So we all know that, if there are any technical difficulties, please interrupt me so we can sort this out. Cool, so we all know the deep learning revolution happened. Researchers used to build entire careers out of hand designing image features. And then came deep learning, where there's a shift between engineered features and learned features. So things like SIFT and HOG transitioned to neural networks. And the general principle here was given enough data and compute, these learned functions outperformed even the best hand design methods. And now, almost no one has a job designing these hand designed features anymore. It's entirely these neural networks, or almost entirely these neural networks. We think a similar thing is going on right now with respect to meta learning. We still design our optimizers, our loss functions, our architectures, and our regularizers. And even when these things are well motivated, at the end of the day, they're heuristics. So for example, in image classification, we're often optimizing the wrong loss on the wrong data set. What we actually care about is accuracy on some test data set, but what we train on is cross-entropy loss on some trained data set. And these are sort of not the same thing. And we expect there's going to be a similar trend that happened with deep learning here. We're going to be shifting from these engineered learning algorithms, so things like SGD, or the concept of autoencoders, for example, to learned learning algorithms, or things like learned optimizers. Now, this work is about learned optimizers. But before we dive into that, I want to first outline training of a neural network with a hand design optimizer, SGD. We might have some initial weights of some neural network, W0. We can compute some loss with respect to these weights. And then we can multiply that some learning rate and subtract. And this gives us some new set of weights, W1. And we can do this over and over and over again to train our neural network. And at the end of training, we can measure the performance and sort of see how well did our optimizer do, how well did our model do. The idea with learned optimizers, instead of this fixed form update equation, we have some learned update equation, U. And this update equation is a function of types of inputs, gradients, weight values, but it's additionally parameterized by this extra set of variables, theta. And these are the parameters of the learned optimizer. So what do these update rules look like in practice? Well, one type of learned update rule that we explore a lot and use in this work is a PerParameter neural network. So it could be an RNN or a gradient, operates on each parameter independently. To spell out what this exactly means, let's consider that we have our learned optimizer running on an n by m matrix. To apply it, we'll first reshape it to an n by m by 1 matrix. Then we'll apply our network, treating this leading n by m as sort of a large batch size. This gives us some new output. It's only one dimensional. And then we'll reshape it back and apply our weight update like that. Now, all that's left is to update the weights of the learned optimizer, updating these thetas. And for that, we can use our measurement of performance that we already had to somehow inform how to update this theta. And then the next time around, we'll do better, and so on. And you just over and over and over and over again until you finally have a good performing learned optimizer. So up until this point, there's been pretty limited adoption from learned optimizers. And we hypothesize one big reason for this is the overhead of using them is just too high. There are two kinds of overheads we explore. The first is memory overhead. This is the amount of extra memory it takes to run this optimizer. This is not a foreign concept, as hand design optimizers also have these features. So things like SGD and Momentum, for example, have one additional copy of memory required, the momentum. Things like Atom, for example, have 2 additional copies. Whereas past work in learned optimizers has been as high as 20 times as much memory. And this is simply not tractable. Next, there's compute overhead. So the time to compute one update is the time to compute the gradient plus the time to run the optimizer. Now, normally, the time to run the optimizer is ridiculously small because these updates are just a handful of operations. But for learned optimizers, we can kind of make this piece arbitrarily complex. And it now becomes a balance to make this fast to run, but also performant. If it was too expensive, we could just run our baseline optimizer and take more gradient steps, for example. And we explore these trade-offs and sort of use the understanding of these trade-offs to design new learned optimizer architectures. One tool we use to explore this is Cradle optimal frontiers, and we explore two of them on this slide. So on the left, we're going to look at memory overhead. On the x-axis, it's the amount of memory each learned optimizer uses. Each color is a different optimizer, hand designed and learned. And on the y-axis, we have the meta loss, or how good these optimizers are. In this upper left-hand quadrant, we can see hand design optimizers. These things use low amounts of memory, but are relatively poor performing in terms of optimization performance. On the far bottom right, we see prior work in learned optimizers, which uses a lot of memory and works quite well, but it's sort of not where you want to be on this trade-off. You really want to be in the bottom left. And this yellow dot is the optimizer that we propose in this work. Similar story for compute overhead. Now, instead of the x-axis being memory, we should have the x-axis being the time per step. We see again, hand design optimizers are in the upper left here. You have expensive learned optimizers in the bottom right, and then our optimizer is yellow dot and sort of closer to the Pareto frontier. Now, to design these optimizers and to design the optimizers we use, we built off of a PerParameter MLP. And this PerParameter MLP can take in a variety of different features. So on this plot, we sort of ablate different sets of features and explore how they land on this memory loss trade-off and compute loss trade-off. Unsurprisingly, if you use all the features, which is this teal dot, you use a lot of memory and are quite expensive, but you work quite well. And sort of the less features you use, the faster you are, the less memory you are, but you might not perform as well. One sort of best of both worlds feature we found are actually leveraging features from Addifactor. And this is this red plus here. And we found this red plus sort of strikes a nice balance between using not a ton of memory and not being fast, but also performs quite well. The next thing we look at is the size of the MLP. So I mentioned before, these are PerParameter MLPs, and we have control over how big that MLP is. One thing that surprised us a bunch is that we can get away with really, really small MLPs and still perform better than a pretty strong baseline. So a baseline run, which is a hand design optimizer, is shown in purple here, and we show the performance of a learned optimizer with respect to different hidden sizes. Now, again, using a larger hidden size does work better, but as we'll see in a second, that can be expensive. But surprisingly, these really small hidden sizes work quite well. Now, how does this correspond to wall time costs? We plotted the performance of each of these different hidden sizes with respect to wall clock time for two different implementations. And what we find is if you're sort of clever and careful, you actually can get speedups from these small models, which is great. So in addition to understanding how the features of the learned optimizer scale, we also wanted to understand how the tasks we apply them to change the sort of calculus of when you might want to use a learned optimizer or not. So first, we can look at batch size. Now, as I said before, the time per step is the time to compute gradients plus the time to run the optimizer. And when we increase the batch size, we're increasing the time it takes to compute the gradients by potentially a lot. And thus the time it takes for the optimizer stays constant and sort of the overhead shrinks. So unsurprisingly, for all optimizers, both learned and non-learned, as we increase the batch size, the overhead over SGD shrinks for these two models. Next, we look at the hidden size. And for here, the type of model matters. So I'm showing an MLP here and a component here. For the MLP, as we increase hidden size, basically all optimizers, including Atom, grow in this overhead, which is interesting. But for this ConvNet, the optimizer that we propose, this red line, actually shrinks as a function of hidden size, which means it's going to be more and more applicable for larger ConvNets as they grow larger. We also plotted out some of these overhead on much larger models, just to give a sense of how the timing breaks down in that setting. And it varies, unsurprisingly, but overall, we think these results are promising. For ResNet 18 and ResNet 50, the overhead is under 50%. For transformers, we only start to see bad overhead when we're using a very small batch size. So for example, a batch size of 2 is about 2.4 times the cost. Putting this all together, we can now look at some training curves. So we tested on 2 models, a Fashion MNIST MLP and a CFAR10 ConvNet, and trained a bunch of different baselines as well as our learned optimizer on them. In terms of steps, our learned optimizer always performs better than all these baselines. This is figure A and figure C. In terms of wall clock time, it now depends on which problem you're training on. For MNIST, we do better than sort of the more simple baselines, these top 3, but not as good as our best baseline. And in the ConvNet case, we still outperform all the baselines. Great. So one other thing that this work does that I'm particularly excited about is trying to make learned optimizer research more accessible. All the code, all the methods are all open source in this package. It's a software library written in JAX. We have learned optimizer architectures. We have various different tasks, including the ones we trained here, as well as a bunch of different training techniques to train learned optimizers. And sort of what we've tried to do with this paper and with this library is to switch the effort required to train a learned optimizer from needing big clusters of machines that are sort of painful to set up to being able to do it in a CoLLab in a couple minutes, essentially thanks to JAX. So with that, I will end, and I'm happy to take any questions. Thank you.
All right, still yell. You mentioned a lot of times in the optimization, we're doing optimizing on the wrong loss function and the wrong data. If we use that loss function and data to train the optimizer as well as the parameters, aren't we kind of exacerbating that problem?
So one cool thing about learned optimizers is that you can train them. So your measurement of performance can be whatever you want. So going back to that example, you might care about optimizing test accuracy, right? Well, you could train an optimizer specifically to perform well on validation accuracy. And then there is still a little gap between the train and test, but the idea is you're training the optimizer to generalize at that point. Does that make sense?
Yes. Any other questions?
Okay, let's thank the speaker again. And we'll